All right, let's start with the exercises. Okay, x plus y is equal to 0. X implies y is equal to 0, right? Yes, so y is equal to y plus 0 by definition of 0, right? And 0 by definition is equal to y plus x minus. So this by definition of 0, by definition of inverse. And this is equal to x by what's given to us. So x minus x, and that's equal to 0. There you go. So that's the first part. So 0 times x is equal to 0. So x plus 0 dot x, yeah, is equal to x dot x plus 0 dot x by distributive property. And this is equal to x dot x as x plus 0 is equal to x. And that's equal to x. And by the first problem, since x, uh, x plus y is equal to x, y is equal to 0. So 0 dot x is equal to 0 by the first column. Okay, minus of 0 is equal to 0. All right, so how do you find minus of 0? So 0 minus 0 is equal to minus of 0, as 0 is the identity element, and that's equal to 0 as any number added with its inverse is going to be 0. So we directly get it. Minus of minus x is equal to x. All right, so x minus x, no, not that. Minus x plus minus of x is equal to 0, correct? All right, so now we are free to add x to both sides by the cancellation law, so I'll just prove that right now. By the axioms alone, b plus a is equal to b plus c if and only if a is equal to c. Why is that? That's because, let's see, yeah, a is equal to b plus a minus b, rearrange it, whatever. And that's equal to b plus c minus b is equal to c plus b minus b is equal to c, right? And it goes backwards too. So you can just do the same thing with b plus c is equal to b plus a. You're allowed to substitute because that's exactly what equality means. So this proves the cancellation law, and you can do the same thing for multiplication. So now that we've proven the cancellation law, which the book also does, I think, we can just add x to both sides. X minus x plus, plus minus of x is equal to x, because x plus 0 is equal to x, right? And yeah, we can just rearrange. I'm using commutativity implicitly. I'm just skipping a lot of steps here. But yeah, if you want to write it properly, then you have to use every law every time. Anyways, yeah, so this is the identity by definition of inverse, and therefore what do you get? 0 plus this number, which is equal to minus of x is equal to, right? Yeah. Okay. So x y plus minus of xy is equal to 0 by definition of inverse. Now, all right, so x into y minus y is equal to xy plus x into minus y. And this is equal to x dot 0, which we've proven to be 0, right? That's there. Now, since the inverse is unique, these two have to be equal, right? That's another axiom. So that means x minus of xy is equal to x into minus y. And through a similar approach, if we take x minus x into y, we'll get minus of xy is equal to minus x into y. It's the exact same proof, all right? All right, minus of 1 into x. Just letting you know, I spent time and solved these problems before this one, so don't judge yourself too harshly if you can't solve it immediately. All right, so how do we get this? Let's see. Yeah, so minus of 1 dot x, right, is equal to minus 1 dot x, right? Is that what we wanted? Yeah. Hang on, what is it asking for? Yeah. So this is equal to minus of x, as 1 is the identity element, which is equal to minus x. And this is exactly what we wanted, right? And this is since we proved the previous problem. Yeah, so this is an extension of the distributive law. So this is equal to x y plus minus of z, and that's equal to x y plus x into minus of z, right? Why? Because of the distributive law, so we can use it for all real numbers, but we have to treat the real numbers. We can't change the plus yet. So this is equal to xy plus minus of xz, right? Now, what did you want to show again? Oh yeah, this is precisely equal to minus xy minus xz, right? By definition. So yeah, we're done. So it is holding, but we have to show it first, and we showed it using the additive distributive law. All right, minus xy, yeah. So minus of x plus y, let that equal to z. All right, I'm just treating it this way. Okay, now what do we have to show? We have to show x equal to minus x minus. Okay. All right. So yeah, we'll take the quantity minus x minus y, and we'll add plus x plus y to it, right? And I'll just rearrange the brackets, and it's very easy to show that it's equal to 0, right? Now, by the uniqueness of inverse, the minus of minus x minus y is equal to x plus y, correct? And by the problem we solved earlier, minus of minus x plus y minus y, right, is equal to minus of x plus y. And this is equal to minus of minus, like this quantity, because we're allowed to cancel two minuses because of what we proved earlier. And this is exactly what we had to show. So we're done. Did it rearrange the brackets? In a normal group, we'd have to, but I think we're fine here. All right. The, yeah, it's the same problem again. So x is not equal to 0. X dot y is equal to, what is it, x? Yeah, x. X implies x y is equal to 1. All right. So x is not equal to 0 implies there exists, I'm going to call it z now, equal to x inverse. So I'm going to use this notation instead of what the book uses as 1 by x because there's going to be a confusion later down the line. So this is exactly z such that x dot z is equal to 1. So they refer to the same thing. I'm just using a different notation, right? And you'll see why. Because later on we'll have to discuss 1 over 1. That gets a bit confusing. So it's the same thing. Just remember that. Okay, right? Now we have such a z. So now what? And I just said to prove the cancellation law on your own, you can do that, right? So what does that mean? That means you can multiply it on both sides, right? Okay. So x uh, dot x inverse dot y is equal to x inverse dot x, right? And this by definition is equal to 1. Dot y is equal to 1. And in this case, y need not be equal to 0 or not equal to 0 for the next step to work. So y is equal to 1 by definition of identity. So we're done. Should I? It should be fine. Yeah. Let's see. X dot x is equal to 1. So x times, so how is it defined? I'll just check what the book defines to the quotient to be as. Yeah. Okay. So x by x is defined by the book as x dot x inverse essentially, right? That's how it's defined. So I actually just used it, but if you want a proof again, I'll just yeah. So it actually follows directly from the definition. That's the problem. So since x is not equal to 0, there exists 1 by x. So you have to check that there exists x inverse such that x dot x inverse is equal to 1, right? And yeah, it's too direct. Yep, pretty much. It's obvious. It's just asking you to state the definition, I guess. But yeah, it is a law and you can use it ultimately. All right, this one is a bit tricky. Let's see. Took me a while on this one. So x is not equal to 0, y is not equal to 0 implies x dot y is not equal to 0, right? Okay, so let x dot y equals to 0, right? Towards the contradiction. So hmm, yeah, I'll have to think again. So, okay, I think I got it. It's slightly tricky, but let's see. So since x is not equal to 0 and neither is y, there exists an x inverse and y inverse, which is I'm just denoting it as the inverse that's in the axioms. You can stick to 1 by x if you want. So the book tries this instead of this to avoid confusions, right? To differentiate between the quotient and the inverses. Anyways, so yeah, xy in dot x inverse is equal to 0. Since xy is equal to 0, we're assuming towards the contradiction that xy is equal to 0, right? What does that mean? That means x inverse, yeah, so yeah, we've got that, and this is equal to y, right? So y is equal to 0. Yeah, and if and that would contradict so there is no contradiction to the existence of y inverse here, to the existence of x inverse here if x inverse isn't zero. But yeah, and similarly, we'll also have, right. So what does that mean? That means so now we have to use a bit of logic here. So let's see. Let's say both x and y are not equal to zero, right? That means both of them have inverses, right? So we should be able to use both of them, right? But yeah, y ends up being zero, which is a contradiction, and x ends up being zero, which is a contradiction, right? Let's suppose one of them is non-zero, then we have no problem essentially. So the second part, which I just mentioned, is not really a proof; it's just a verification. But the first part is the real proof, since we had a contradiction for x, y not being zero. So what we just showed was x, y equals to zero implies either x or y are zero, right? So it's slightly trickier, but not that much. It's just a bit of a extra logical leap. That, and we're using the lemma of zero times any number is zero. Of course, a real number. Yeah. Okay. Okay. So I'm just writing it in another form, but it's the same question. All right. So how do I show this? So I'm going to call the one. I'm going to call it equal to x, right? Now, observe that. Okay. So yeah. So we're given that y and z are both not zero, right? That's important. That enables the existence of this quantity. And of course, with the previous lemma, we also know that such a quantity exists because yz is also not equal to zero. So that's why it was important, right? Okay. So x times y times z is equal to 1. Observe that, right? So y times y inverse and z times z inverse and the commutativity. So what does that mean? That means x is precisely equals to yz inverse, right? It's by definition of what the inverse is. So you can just put brackets here, right? So I'm using many of the laws implicitly. Yeah, sometimes there's associativity, but because of commutativity, the whole operation becomes a lot simpler, right? Okay, x dot y inverse plus w dot z inverse is equal to xz plus wy y yz. Uh, all right, so let's go in the similar procedure. So the left hand side is equal to, let's say, theta. Okay, so theta times yz is equal to what? Is equal to x dot z plus w dot y, correct? Yeah. So what does that mean? That means, yeah, theta, since y and z are given to not be zero, so the same argument, theta dot y dot z dot y dot z inverse, which exists now, is equal to x z plus w y z inverse, right? And this is equal to theta, which is equal to the left hand side. So theta is equal to this, which is exactly the question. Oh, I saw D part before H part, or O part before N part. All right. Anyways, x dot y inverse dot w dot z inverse. That's precisely what the question is asking, right? Oh no, it's not. Okay. Never mind. That's fine. Yeah. A is equal to x dot w dot y z inverse. And yeah, the whole point is so this is equal to x dot w dot y inverse dot z inverse. Right? We can just rearrange them. And this is equal to what? This is equal to, can we just show that directly? Let's see. So yz are not equal to 0, right? And yeah, we just showed 1 by y dot 1 by z is equal to 1 by yz. Or this is equal to x dot w times y dot uh, inverse. So yeah, we already showed this. Yeah. So x is not equal to 0 implies x inverse is not equal to 0, right? Okay. Hmm. So if x inverse is equal to 0 towards a contradiction, then x dot x inverse is equal to 0 is equal to 1, right? So yeah, we get a contradiction. So we are free to assume that x inverse exists given that x is not equal to 0. So that's not a problem. The 1 is equal to 0 is the problem. Okay. W dot z inverse whole inverse is equal to what is it? Yeah, z dot w inverse. Okay, so how do we go about this? Okay, yeah, we're going to start this side now. Call it theta again. Theta times w times z inverse is equal to 1, correct? By definition of inverses, and what are we given both to be non-zero? Yeah, both are non-zero. Good. So that means theta is equal to w dot z inverse by definition of inverses. So if I okay, now we're doing that one. Okay, x dot y inverse dot w dot z inverse whole inverse, correct? Yeah, is equal to x dot z. Is that it? Yeah, dot y dot w inverse. Yeah, I'm writing it in this notation because there's no one there to confuse us, and that it allows you to see the definition of the inverse a lot clearly. Okay, so how do we go about this? Let's see. So this we just proved is equal to x dot y inverse dot what was it? W inverse dot z. Oh, we haven't shown that, have we? We have not. Okay, so I have to show two things now. So x, hang on, I missed a couple questions. I'll just cover them right now. So first question I missed was, yeah, x dot 1 inverse is equal to x, right? Okay, is that it? Yeah, that's it. Okay. And x is not equal to 1, not equal to 0, not equal to 0. Okay, so first of all, 1 inverse dot 1 is equal to 1 by definition of x times x inverse, and it's equal to 1 inverse by definition of 1. So they're both the same thing, right? Let's get that out of the way. And actually, yeah, right from that, we get that's equal to x dot 1 and x dot 1 is equal to x. That's so go this way. That's the argument. So that's one question I skipped. Anything else I skipped? Nope, 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 nope. Yeah, let's go back. Hang on, I saw that one. What did I want to show now? Oh yeah, right. One x inverse to the inverse is equal to x. That's what I wanted to show. Okay, so yeah, x inverse dot x inverse is equal to 1, right? And x inverse dot x is equal to 1 by the uniqueness. And okay, yeah, these both are true because here the definition of x inverse is the inverse of x, and here the definition of x inverse is the inverse of x inverse, right? So we're using the definition of inverse here and here, and they're both equal to 1, right? And by uniqueness of inverse, x is equal to x inverse, right? Okay, so this is just an extra question I introduced, I guess. It's worth solving, so if you could solve it before me solving it, that would be nice. But yeah, now that we've done that, I can easily show x dot y inverse dot w dot z inverse is equal to x dot y inverse dot w inverse dot z inverse. And that's equal to x dot z dot y inverse dot w inverse. And through what we showed earlier, since and z, w aren't 0, their inverses aren't going to be 0. Sorry. Since and w and z are all not 0, their inverses are not going to be 0, and we can work backwards too. Since z inverse and y inverse and w inverse are not 0, y and w are not 0. So all of that is used here. So what do we get? X dot z is dot y dot w inverse. This is equal by what we showed earlier, right? Okay. A dot x dot y inverse is equal to a dot. Essentially, the problem is just asking us to verify associativity. So I was using it implicitly so far, but yeah, it is literally just associativity. And yeah, I did skip a lot of steps here, but it's fine. Okay, so what do we have? Minus x dot y inverse. Is that ever there? Yeah, is equal to x dot minus y inverse is equal to minus x dot y inverse. That's what we have to show. All right. So we do know, yeah, this part is trivial by the exercise we solved earlier. Since xy and xy inverse aren't that different, we can just substitute variables. So this part is trivial. Now for this part, we can use the other part of the problem, which is this is equal to x dot minus of y inverse, right? Now we have to show that this is equal to this. So I'm just going to directly prove it. Minus of y inverse is equal to minus y inverse, right? Okay. So for this, let's see. So y isn't 0, minus y isn't 0. Yeah, we can directly use something here. Okay. 1, no, minus y whole inverse plus minus of uh, y inverse. Hang on. Let's see. Okay, y inverse plus minus y inverse. What is that equal? Minus y, the minus y is inverse. Okay. Now here we need to use the lemma. Yeah. What is that lemma? We have I'll just check. Yeah, we get minus y plus y by y dot y. Correct? Minus y dot y. I think that should be correct. Or to rewrite it using my notation, we get minus y dot y inverse. Yeah. And this is equal to 0. So 0. So that we get 0 dot some real number which exists because y is not 0. So we get 0 dot delta, which is 0. Yeah. So what does that show? That shows that by definition of 0, minus of minus y inverse is equal to y inverse. And from that, we can just use the same property we used. So yeah, it shows that these two sets are equal. Uh, well, technically set, but yeah, numbers are equal. And that shows this. All right. Okay. Prove the following laws of inequality. So I'll just restate the laws of inequality for reference. X plus x greater than y implies x plus z greater than y plus z. This applies for all real numbers. And x dot x greater than y implies, and yeah, implies. All right. So you've gotten this out of the way, and I'm just going to keep these axioms in here for reference. Okay. So x greater than y and w greater than z, z. So what we have? Yeah. Okay. So how do we show this? Let's see. Okay. By the first law, w. How do we do this? Yeah. X plus w is greater than y plus w by the first law, right? And by the first law applied here, again, x plus, or is it? Yeah, yeah, x plus, no, sorry, yeah, y plus w is greater than y plus z. So I'm adding, essentially, I'm adding y to both sides here and adding w to both sides here. And since the order is a transitive relation, we get x plus y is greater than y plus z, right? Okay. Okay. Yeah, and using the same thing, we can just use the same problem. So okay, x greater than 0, y is greater than 0. So taking y as the, so x is x, y is 0, and z is y. we get x dot y is greater than 0 dot y, which is equal to 0. So x dot y is greater than 0, right? That's one of them. And for the other one, since we generalized it, x is greater than 0, y is greater than 0. So x, y, w, z. So we get x plus y is greater than 0 plus 0, which is equal to 0. So x plus y is greater than 0, right? It's the same thing. Yeah. Okay. X is greater than 0 if and only if minus x is less than 0. All right, let's see. So x is greater than 0 implies x plus minus x. Let's see. I'll have to think. Hmm. Okay, so towards a contradiction, let minus x be greater than or equal to 0, right? So let's get x minus x is equal to 0 out of the way. Uh, yeah, that just means what? That means minus of x is equal to 0, which implies minus of 0, which is equal to 0, which implies x is equal to 0. So we get a contradiction already. So x cannot be greater than equal to 0. And if minus x is greater than 0, then what we get? Then we get, yeah, then we get x plus minus x is greater than 0 by the previous property. And that means 0 is greater than 0. But the order relation is irreflexive. So that cannot happen. Irreflexive, non-reflexive. Either way, it cannot happen, and we're getting a contradiction. So, all right. Yeah, so we can just do a trivial substitution, using the fact that minus of x is equal to x, we can just take minus x to be y and use the property and prove the converse. Okay. Yeah, x is greater than y if and only if minus x is less than minus y. Is that it? Yeah. So how do we show it in the cleanest way? Yeah, okay. So x is greater than y implies x minus y is greater than 0 by adding is adding a constant to both sides, right? Because yeah, nothing's stopping us. It will preserve the inequality. And from this, we can use the previous problem, which implies minus of y minus, right. So I'm using two properties at the same time here. Minus of x minus y is less than 0. That's one thing. And this entire thing is equal to minus x plus y is less than 0, right? And now I'm adding it again to both sides. So what are we adding? Yeah, which implies, hang on, did I change something? Yeah, it's fine. Which implies minus x is less than minus y, right? By adding minus y to both sides. So yeah, it should be fine. Okay, yeah, x greater than y, z is less than 0. So that means minus z is greater than 0. So that means x dot minus z is greater than y dot minus z, right? Which means minus of x dot z is greater than minus of y dot z. We proved the property just now, right? This is the same thing. And this means, well, we can flip it. We can write minus of yz, sorry, xz. is less than minus of y0. We're just using the previous question again, right? So this means x dot z is less than y dot z. So we're using, yeah, we're multiplying it. We're using the same rule essentially, but with a minus z instead, right? Yeah. So we're using nothing but the rules we've either already proven or, you know, the rules we're given. That's all. That part is very important. Okay. X is not equal to 0, so we will use it in the contradiction. And x dot x is greater than 0. So, okay. So by totality, either x is greater than 0 or x is less than 0, right? Because this is a total order relation. So in this case, we can directly use this. So x dot y is greater than 0 and y here being x. So x square is greater than 0. So it's the same thing. Now in this case, minus of x is greater than 0, right? So minus of x dot minus of x is greater than 0. So what is this? This is equal to minus of x dot minus x, which is greater than 0. And this is the same as minus of x dot x, which is greater than 0. And this is equal to x dot x greater than 0, right? So I'm only using the entirety of the properties that were proven for without order. So, minus of x is x. That is being used here. But yeah, ultimately, in the long term, just forget about it. The important things are, you learn how to prove things. And yeah, you just use these properties freely for real numbers. Okay. Yeah. So as a result, what we get? We get, yeah. So 1 dot 1 is greater than 0 since 1 is a real number. And that's equal to 1. So 1 is greater than 0. And by the property proved earlier, minus 1 is less than 0. Yeah. And we can just write it all together. That's all. Okay. Xy is greater than 0 implies x and y. So x comma y greater than 0 or x comma y less than 0. Okay. XOR is just the exclusive or that's all. Okay. So towards the contradiction, let x be greater than 0 and y be less than 0. And then that's case 1. And case 2 is x is less than 0 and y is greater than 0, right? Now, I believe we can just use here we can directly use what? Yeah. So we had a theorem about z being less than 0 and x being greater than y, and then xz being the inequality being flipped. So we can directly use that theorem here, and we'll get x dot y dot x, which is equal to x dot y, is going to be less than 0, which is a contradiction. So we're done. And here we can use the same theorem, but in the other direction. So x dot y is less than 0, which is also a contradiction. And realize that this is the exact opposite of this. You'll have to use truth tables again. That's one way of doing it. Right. So x greater than y is greater than 0. So I'll just write them all down for a second. X greater than 0, y is greater than 0, x is greater than y. Y. Yes. Now we need to show 1 by x is less than 1 by y. So we have to show that the inequality flips. Okay. So I don't think I'd want to prove it by contradiction. So what can we do? Yeah. Okay. So this, uh, have we proven that 1 by x is positive? We haven't, right? Yeah, I just have to do that. Sorry. Okay, let's prove 1 by x is positive. So x is greater than 0. Uh, 1 is greater than 0. So x, this implies x is not equal to 0, which implies x inverse exists, right? Okay. Now, hmm, how do I do it without contradiction? All right, I can write this as x dot x inverse, right? And since x is greater than 0, I can write this x dot x inverse is greater than 0 implies x is greater than 0. Sorry. Um, oh, yeah, I can wait. No. Yeah, this isn't the way to do it. Yeah, it exists, that's for sure, by totality. Okay, so towards the contradiction, let x inverse be less than equal to 0. If x inverse is equal to 0, then 1 is equal to 0. That part I'm just leaving out, right? If x inverse is less than 0, then x dot x inverse is going to be less than 0, right? So 1 is less than 0, which is a contradiction to the theorem proved earlier, right? So by contradiction, this is false, and the only way this can be false is if x inverse is not real, or since it is real, x inverse is greater than 0. Yeah, I don't know what I said. I mean, it's true, but to an extent. But yeah. So now that we've proven that x greater than 0, y is greater than 0, x is greater than y. So that means what? That means 1 by x is greater than 0, 1 by y is greater than 0. And multiplying a positive quantity on both sides, we get 1 is greater than y by x, right? And multiplying a positive quantity on both sides again, we get 1 by y is greater than 1 by x. And sorry, I meant, right? Okay. But yeah, ultimately, it's not too hard to prove 1 by y. So that means 1 dot is equal to 1 by dot y inverse is equal to y inverse. So the notations are equivalent, right? Like this is what we would think 1 by y is, right? And this is what the book is writing as 1 by y, right? Ultimately, the notations don't matter now, at least in the structure we're dealing with. Okay. Okay. Sorry about the break. Okay, yeah. Sorry about the break. Yeah, just had a small thing. Okay. X is what, greater than Y? No, less than Y. Okay. And we have to show that X is less than X plus Y by 2 less than Y. Okay, so we add, is anything given about anything here? No. Okay. Hmm. All right, the inequality is preserved on adding. That's fine. So X plus Y is less than Y plus X. That means 2 times X. Oh, we don't have that. So have we defined X plus X is equal to 2? We have defined 2. So okay, we can use this. X into 1 plus 1, right? We can use this. How will I show that? Okay, I'll just write it down properly, but should be fine. This is equal to X dot 1 plus X dot 1 is equal to X uh, dot 1 plus 1 is equal to X dot 2. By definition of 2 is equal to 2 dot X, right? Okay. Now, which implies X is less than Y plus X dot 2 inverse. Yeah. Also, yeah, the reason I'm writing inverse is also because of what the question later states as, you know, the inverse. Like it says a to the power minus n is equal to 1 by a to the power n, right? So the notations are just notation and they end up being the same thing. Yeah. So don't confuse my inverse notation with this thing, right? Like this is still being defined as the unique number that such that x dot y is equal to 1, right? So that hasn't been changed here. So 2 dot 2 inverse or 2 dot 1 by 2 is equal to 1. That's how it's being defined. Okay. So we proved one side, and to prove the other side, we use the same argument, but we add y to both sides. So x plus y is less than y plus y is less than 2 dot y, and we get the same thing, right? So we can just, this is equal to x plus y dot 2 inverse by commutativity. Yeah. So x, this, right? If you want, same thing. So that's how you prove that. We'll get to density in a while. Okay. I hope I didn't leave anything. Yeah, I didn't. Okay. So show that the intersection of a collection of inductive sets is an inductive set. Okay. So let's see. I'm going to call this a collection of inductive sets, and you have to show intersection A belongs to alpha. A is inductive. Okay. And I'm going to call this B. So one belongs to A for all A in alpha as A is inductive, right? And this is precisely what it means for one to belong to B by definition of the intersection over collection sets, right? Using the first order property. Okay, so one is in B. Now we assume X is in B. Now if X is in B, so this can happen if and only if X belongs to A for all A in alpha, right? And this can only happen if so X is in A. Hang on, yeah. This implies that X plus 1 is in A for all A in alpha by inductivity of each A in alpha, right? But this precisely is equivalent to saying that X plus belongs to B by definition of intersection. So to summarize, x plus x belongs to B implies x plus 1 belongs to B, which is precisely what it means to be inductive. So that proves the first part. And since Z plus is the intersection of a collection of inductive sets, that also proves the first part of the second part, which is saying that Z plus is inductive. Now, oh, right. I had to prove 4.1 and 4.2. I'll do that. Okay. Yeah. So the only way I can interpret the question is if what is it's saying is if A is a subset of Z plus and A is inductive, then A is equal to Z plus. That's the only way I can interpret the property. Right? If there's another interpretation, do let me know. But this is the best one I can think of. So, hmm, yeah. And Z plus is defined as the intersection of all the subs inductive subsets of real numbers. Right? Inductive subsets of real numbers. But this is a subset of real numbers by definition of since R plus is an inductive set of real numbers, so which is a subset of R by because it's containing all real numbers such that something is satisfied. So this part is trivial, and this part is through intersection. And by transitive property, therefore, A is a subset of R that is inductive, right? And by definition of intersection, by the property, if yeah, so since A is contained in this set, the intersection must be contained. The intersection must contain it. So in generality, if like yeah, if any one thing is in the intersection, then this must be contained in it. So what do we get? We get Z plus is contained in A, and both of them together mean that A is equal to Z plus, right? That's yeah. So we're using subsets here. This is true because this is x belongs to R and x is greater than 0, right? So it's a constraint, it's an extra constraint, so we get a subset, right? And this is the intersection of such sets. So yeah, this is trivial, right? And this is transitive. I think I showed it, I'm not sure, but just see the methods of exercise 1. And since by transitivity, we get A is a subset of R, and A is an inductive subset of R, and Z is the intersection of all the intersection of collection of collections of all subsets of R which are inductive. And yeah, so I'll just check the intersection thing. Have I actually proven it already? Let me just check that. Yeah, we have to use 5C from exercise 1. So from that, we can prove it directly because X must belong to A for at least one A in alpha in the collection. So it is belonging to at least one A. Yeah, I am not expanding further. Yeah, it's fine. So that's the basic properties proved by, okay, now I'll prove 4.1 and 4.2. Okay, so every non-empty subset has a least element. So by induction, we'll prove that every section has a least element, right? So the set 1 has a least element because uh, if it doesn't have 1 in it, then it's empty and that contradicts the assumption. And if it has 1 in it, then 1 itself is the least element. So we're good for 1. And assuming it's true for n, then we'll check for n1 comma n plus 1, right? If n plus 1 is in it, then if n plus 1 is the only element in it, then n plus 1 is the smallest element. If it's not, then we can check the smallest element for this set. The I'm going to call it call B a subset of this section, and B intersection with this section is going to be a subset of this, and we have the property valid for this subset, and the least member of this is precisely going to be the least member of B. And why is that? That's because yeah, if it's not the least member here, then it's not the least member here. That's why. And yeah, we just try to show it in generality as if the subset B of Z plus is non-empty, there exists a natural number in B, and we take the section containing that natural number, and since this is non-empty, by our proof by induction, we can take the least element here. So that's how we prove the well-ordering principle. That's theorem 4.1. Now for 4.2, yeah, it just does a direct contradiction essentially. So Sn subset of A implies n belongs to A, but we're assuming A is not the entirety of Z plus, right? Yeah. So that means there exists n that's not in A, that belongs to Z plus, and we'll take, so since n is satisfying this criteria, Sn will be a subset of A, and using this property, it will contradict directly. So that's how we're proving it. Okay. And we'll cover the Archimedean property soon enough. Let's see. Okay. So yeah, let's prove question 4, A part. Every non-empty subset, so B is not phi, subset of Z plus. Hang on, is it a subset or yeah? Is it an Sn plus 1 or Sn minus? Yeah, yeah, yeah. And we have to show this has the largest element. Yeah, so if you want a formal proof for the earlier one, we have a definition for the largest element, right? We have it from the well ordering section earlier. Not well ordering. The what ordering was it? Was it ordering or just yeah? So primum, infimum, that's up. So y is greater than equal to b for all b and b, and y belongs to b. That's what it means, and we can use the properties of ordering to contradict, but it's such a long thing that I'm just not writing it. But if you want to formalize it, that's how you do it. Anyways, so yeah, so what do you have to show? We have to show it's a large. Okay, yeah, and it's not empty. So we start with the set 1, and the largest element is 1, so we're done, right? There is nothing to compare it with, and yeah, now let's take induction.